Thank you all for coming and showing an interest in sea levels and Christchurch, and hopefully you'll get something out of tonight. I'd also just like to introduce, I've got an assistant tonight. This is Christopher Gomez. Us geographers are very collegial and often don't work alone. So Christopher is an experienced tsunami researcher, flood modeller. The cleaners in our department will attest to that. And he's going to be helping me out with a demonstration tonight. So what if Christchurch's sea levels rose higher? In my abstract, I talked about snapshots that we get in the media, pictures of sea level rising, and this is the kind of illustration that you'll find in the paper or in the media about sea level rise. And it's in fact a storm, which on the surface seems like a different topic. It seems like, why would you illustrate sea level rise with a storm? But I'm going to try and explain the link between them and look at variation as well as rise in sea levels. Also in my abstract I had 3 questions. So the format for tonight, first of all we're going to look at the physical processes behind sea level rise and variations in sea level. So I'm going to address those 2 things. And then I'm going to look at how coasts respond. The coasts are very active. They don't just sit there and accept a rise in water level. They've got dynamics and processes that help them to adjust in response to water levels going up. Then I'm going to mix it up and make it more complex by looking at a bunch of different hazards. How do rising sea levels interact with things like floods on land, earthquakes, tsunami, a whole bunch of different things in a package that we call Multihazards, and I'm going to talk about some recent research projects. Before I get into the details of the processes behind sea level, it's always good to define what sea levels are. What am I talking about when I mention sea levels? So you'll often hear people talking about sea levels, and they might be either talking about absolute water levels or relative sea levels. So the next 2 slides I'll define that. Absolute sea level is the elevation of the water surface. It's got nothing to do with what's happening on land, whether the land's going up or down. It's just the level of the ocean. Typically we measure this today using satellites, and so we measure it from a theoretical perfect ellipsoid, or you can measure it from the centre of the earth. But it's just the level of the water, not in relation to the land. And eustacy is a word that you'll find associated with that. This is a global snapshot of absolute water levels in our ocean surfaces, and you can see that the highest part in our ocean is here up above Indonesia, and that the Pacific absolute water levels are higher than, for instance, the Atlantic, much higher than the bottom of the Southern Ocean. So water levels today in any one part of our global ocean are different, and part of what I'm going to be arguing today is that we need to look locally. We need to look at what water levels are doing in relation to our land surface, and this is relative sea levels if we're going to understand the coastal response. So relative sea levels, these, for example, are reflected in the water level on our beaches, the water level at the coast. We use tide gauges to record changes in relative sea level. And relative sea level includes the movement of our land. We're all familiar with movement of land in Christchurch, but over geological timescales, land gets depressed or rebounds in relation to ice sheets sitting on top of the land. So the Earth's crust is a little bit like a waterbed. When you put a big weight on top, it'll be depressed, and when you take that ice sheet or that weight off, it'll spring back up. Now, ice sheets melt a lot faster than the land responds. So we had our last glacial maximum quite a few thousand years ago, but our land is still adjusting to the disappearance of those ice sheets. So it's a very slow response, and you've got to take that slow geological timescale response of the land movement into account in relative sea levels. You've also got to take into account things like earthquake movements, which are not quite so slow. For example, Scotland is rebounding. Scotland is slowly rising up in terms of the land surface. So without moving the water level, you've got relative sea level fall in Scotland, fortunately for the Scottish. London, on the other hand, or southern England, is sinking. The land itself is sinking in a response to past glaciation melting off in the region. And so the flooding that you've seen recently in London, all of those things will only get worse as London keeps on sinking, regardless of what's happening out in the ocean. So on top of our present sea levels and our land movement, then we can start to look at what would happen if sea levels were to rise. So what are sea levels up to? Last week, if you saw the media, there was a lot of talk about the IPCC Fifth Assessment Report. That's the Intergovernmental Panel on Climate Change. They released their fifth assessment looking at what sea levels are up to. And this is one of the graphs, the summary graphs from that report. So they've made predictions about what sea level will do between approximately 2005, that's their base starting level for their models, up to 2100. So over the next 100 or so years, where is sea level going? And you can see that all of those different simulations, these models, predict a rise in sea level. The different colours represent different carbon emission scenarios. So if we don't emit so much carbon, we'll get sea level rise somewhere in the range of about 30 centimetres. If we keep on emitting a large amount of carbon into the atmosphere, they predict that we're going to get anywhere up to a metre by 2100. Now these are global predictions, and I've just been saying we need to look locally to understand what's going to happen with sea level on our coast. So in the New Zealand region, the predictions from Rob Bell at NIWA are that we're going to have a rise of anywhere between 70 centimetres and a metre. That's the average sort of predictions up to 2115. The range is anywhere from half metre up to 2 metres. So we could get sea level rise in exceedance of 1 metre, we could get less than that. But the Ministry for the Environment uses 1 metre as a sort of safe sea level rise prediction for 2115. But haven't sea levels been rising for a long time? For example, since the last glaciation, I mentioned that. These are the absolute global sea levels, the rise that we've had across our interglacial, the Holocene, since the last glacial maximum. So here we've got the present day, and we've got thousands of years before the present day here, and sea level change in metres. You can see that during the last glacial maximum, sea levels were a lot lower, 140 metres or so lower, and the edge of our continental shelf off Canterbury gives us an indication of where the water would have got to. And we've had some very steep rises throughout the last few thousand years, and then a tailing off, but we've still got a little bit of a rise in absolute global sea levels going on there. That's a background Holocene adjustment in our ocean basins, and this is an underlying sea level rise that we have to put any anthropogenic or any human effects on top of. So we have to account for this underneath any climate change induced sea level rise that we're going to add to it due to human effects. But weren't sea levels a lot higher for most of time on Earth? Some people will say we shouldn't worry too much about sea levels rising because for most of Earth's history, 542 million years, sea levels have been 50 to 200 metres higher than present. So here we've got present at this end of the graph, humans, Homo sapiens appear about here, 542 million years, a lot higher sea levels for much of that time. But that doesn't really tell us much about our Earth today. This was a time when ocean basins were deeper. The continents had a different configuration. We had things like Gondwana land, we had dinosaurs. So it's quite relevant to dinosaurs, but it's not terribly relevant to our present situation where we have populations concentrated around the coast, where we have coastal megacities. For example, in New Zealand, 75% of us live within 10 kilometres of the coast, and that wasn't going on for most of this time. So I think we can discard that argument for now. Another argument is looking at sea level rise over the next century. Isn't 70 centimetres or a metre scaremongering? Isn't that sort of overestimating sea level rise given the last century's rates of rise. So let's look at the last century's rates of rise. Over the last century in New Zealand, we've had a relative trend of sea level rise of 1.7 millimetres per year. Tiny fraction per year, but that adds up over time. About 17 centimetres over the last century. In our Canterbury region, if we take account of the sinking of our local part of the South Island, we can estimate sea level rise over the last century of about 19 centimetres. So we've had 19 centimetres of sea level rise. In the record up to 2000, we hadn't started to detect an acceleration of sea level rise due to anthropogenic or human-induced climate change. We're starting to detect that now in the last 10 years of record. So this is the underlying sea level rise that we've got to account for across the Holocene. And I'm going to look at the difference between sea level rise and variation in sea level for this part of my talk. So we've got underlying sea level rise, and we've already had that, 19 centimetres over the last century. We can put IPCC predictions of about a metre on top of that, but water levels also vary every day, every week, every month. So I'm going to get Christopher to demonstrate the last century of sea level rise. Got our sea level rise here in the blue dyed colours. So that's our 19 centimetres for the Christchurch region. And if you could put the next 100 years up to 2115 on top of that. So these are our mean levels of ocean water at the coast, our mean sea levels. But mean sea level is not the story that you'll see any one day when you go out to the coast. You'll see mean sea level plus or minus the variation of a number of other processes. And so we'll add those in as we go. Just on this graph, the separation of these lines is artificial. That's just that we can draw the lines out and see the differences between them. So don't think that Wellington's better off than Auckland. We've just pulled those lines apart. What I would like you to note is the difference in the trend. So that's our smooth linear increase here, and the variation about that trend. So in any one year, you might find that our local sea level is quite far from the average trend. And we're going to look at the processes that cause that over time. One of the processes that causes that is ENSO, or El Nino Southern Oscillation cycles. So here we've got some satellite data, an El Nino year and a La Nina year. During La Nina conditions, we have a set of winds which pushes water, warm surface water, across the Pacific from South America over here, and it pushes it towards Indonesia and Australia. So you get all of this water stacking up on our side of the Pacific, and the sea levels go up on our side of the Pacific. They go down off South America, which leads to upwelling and a good anchovy crop. Then El Nino comes along, and the wind systems that drive or are coupled with the ocean circulation break down, and the water sloshes back across the Pacific. So the sea level across the Pacific seesaws and changes under El Nino conditions. So we've got all of our warm surface water heading back across towards South America. The sea levels in South America go up, our sea levels go down a little bit, no space for upwelling, no anchovies. And variation in sea level. In our region, the ENSO effect plus the variation in ENSO at about the 20 to 30 year time scale, called the interdecadal Pacific oscillation, is about plus or minus 25 centimetres, so about 50 centimetres in total. You get cycles between El Nino and La Nina anywhere between 2 and 4 years conservatively. The strength of El Nino and La Nina cycles, though, varies with the interdecadal Pacific oscillation over about 20 to 30 years. If we look back at records of sea level and temperature in the oceans over the Holocene, we can see that there's probably also a larger cycle happening at about the 200-year scale. So there's a lot of variation here in this one big ocean atmosphere circulation system across the Pacific that affects our sea level. So I'm going to get Chris to put variation in a different beaker, and we've got green colours for sea level variation. So depending on whether we've got El Niño or La Niña conditions, we might have this water on top of our base level, our mean sea level in the blue, or not. We've also got tides. So I was talking 2 to 4 years there. Every day we have tidal water variations. And in Canterbury, roughly about 2 metres variation in the elevation of the water surface at the coast. So we've got NIWA's tidal predictor here across our current month, and you can see the high waters and the low waters, and roughly we've got about 2 metres variation. So we can add 2 metres to our variation in our mean sea level, or plus or minus one metre. Now you can see that the tides across a month vary quite a lot. So you might have heard of spring tides and neap tides. Spring tides are when the moon and the sun line up together and their gravitational pull works together to pull the water in the oceans and give us bigger high tides and lower low tides. When they're on opposite sides, opposite axes of the Earth, they're fighting against each other gravitationally, then we get a dampened tidal signal during our neap signals. So we get high tides, but they're not as high as during the springs, and low tides, but they're not as low. Much harder to do coastal fieldwork during those conditions. Now that's what you'll learn in the textbooks, but in Canterbury we've got an extra very interesting layer. And I do some work with some Korean oceanographers, and they think that our tides are very weird because we also have the apogean and the perigean effect. This is basically the moon's orbit of Earth brings it at some point quite far away from the Earth and at some point quite close. So when the moon is close and you combine that with the moon and the sun lining up, you get these mega spring tides, and when the moon is far away and you get the moon and the sun lining up, you get smaller spring tides. So when you see in the news tidal flooding or big storms coming on top of big tide levels, it's usually under perigean conditions when the moon is close. And this is, it's not unique. We're not the only people in the world that experience this, but it's not the common textbook pattern of tidal circulation. So it's another local process, locally very significant, that we need to keep an eye on if we're going to understand sea level variation. Then we have the atmosphere and storms, weather, that affects sea level. When you have a high pressure system, you've basically got a big heavy column of atmosphere pushing down on the ocean surface, and it depresses the ocean surface a bit by a few centimetres. When you switch between that nice fine weather high pressure system to a low pressure system, often associated with rain and strong winds, it's also a change in the atmospheric column. So the atmosphere is not pushing down, it's low pressure, it's quite light on the surface of the oceans. So the surface of the oceans springs back up. And it's about 1 centimetre of sea level variation for every hectopascal change. So these are the kind of maps that we see every night when you watch the weather. And this is the map from our March flooding event. You can see a low pressure system off here, 992 hectopascals, and a nice high pressure coming from Australia, 1024. Every hectopascal of change there leads to approximately 1 centimetre change in the sea surface. Now when we've got our high pressure systems, that's our nice fair weather conditions. Our low pressure systems, these are our storms. So at the very time when we've got extra rainfall, when we've got extra wind, when we've got all that bad weather, the ocean's surface is springing back up and it's becoming higher. And you can start to see how that would contribute to flooding under those conditions. For the 4th of March event, compared to last week when I was doing this PowerPoint, we could see a sea level difference of 40 centimetres. So that was a drop in sea level from that March event of 40 centimetres because last week's weather was fine. So I'll get Chris to add in, and this is called the inverted barometer effect because it's an inverse effect with the barometer that tells us about atmospheric pressure. So we're starting to build up quite a big beaker full of sea level variation compared to the base level in blue. On top of that, during storms, you get storm surge contributions from wind and waves. So during a big sea storm, you've got large waves trying to push water on land, and you've got winds flowing onshore, trying to push water onshore. And this can lead to a very localised setup or a very localised elevation of the coastal water level just at the coast. During the Wahine storm, they estimate that storm surge contributed about an extra metre of sea level elevation during that storm. So at the same time as we've got really big waves and lots of rain and bad weather conditions, we've got an extra metre of sea level to deal with. During Hurricane Sandy in the States, they estimate that the storm surge was approximately 4.2 metres. So when you saw New York and the eastern northern states in the United States being flooded, part of that was because of this big storm surge. These are just the water level variations. On top of those water level variations during storms, you've got to add in the waves. So Sandy, they estimate the maximum wave heights were around 10 metres. For us, with our March event a while ago, we had wave heights measuring 12 metres off Banks Peninsula. So we've got to add those in on top of that, but I'm not going to do that to Chris today. We'll leave that off. Now we move on to looking at how does the coast respond to our base increase in sea level, and you can relax for a while, thank you, as well as these variations in sea level. I said before that the coast is a very active and dynamic geomorphic system. It just doesn't sit there and get flooded. It responds by processes which can shift sediment and the landscape about to change the shape of our coastline, to change our drainage system in response to more water. So the sharks analogy is a little bit too simple. If we go back over the Holocene, so away from our present timescale, and just look at how our coast has responded over Holocene timescales, just as sort of a snapshot to see how incredibly dynamic our coast can be. We sort of think of this as land as a pretty permanent surface that we're here in today, but it is very contemporary, very recent, and very dynamic in the past and potentially in the future. So about 9,000 years ago, this was our coast. We've got our present shoreline there dotted in so that you can understand how far out the coastline was. So about 9,000 years ago, that would have been coastal real estate. Then, with our Holocene sea level rise, this was coastal real estate here in Riccarton. So you've got your CBD there to orient yourself, and the shoreline 6,500 years ago approximately was pretty much through Riccarton. So we had a retreat of the shoreline inland, and we had inundation. And then over the next few thousand years, up to 2,000 years ago, and then more recently, with the growth of the spit, we've had a progradation or a building seaward of the shoreline. So we live on a very, very dynamic surface that was very recently a coastal feature. And it's been built up with sediments from our continental shelf, with sediments from our rivers. And when you dig down through these surfaces, anywhere east of here, you'll find a lot of coastal and river deposits. These are the kind of deposits that liquefy very well, incidentally. So just setting the scene for a very dynamic city. I'm going to look at two responses to sea level, two groups of responses. The first one is what happens to the water table and the rivers. So we're looking at how the freshwater component of our city responds to sea level rise. So we start off with a base sea level. If we get sea level rise, like that, our water table also responds. Because in the original scenario, the water table has a slope, a gentle slope underneath our land, which runs down to meet our present average sea level. So if we increase our base levels with our blue beaker over here, we increase our water table at the same time. Our water table rises at the same time to come up and meet that rising sea level. So you can see the problems that we've had recently with the earthquakes with high water tables. You can imagine the problems we have with flooding with high water tables. This is one very significant change that you get with sea level rise, and it can go quite far inland. Similarly, our rivers slope down across the plains towards the level of the sea. If we increase the level of the sea, our river channels and our river water levels respond, and they are raised up to match your new higher sea level. So these are one of the kinds of changes that we can expect. Now, Tonkin and Taylor has recently done a report for the City Council looking at if we flood inland on a higher sea level around our two main river systems. So we've got our Avon here and our Heathcote here. The light blue colours are a flooded landscape from a rise in sea level. Now this is a very, very simple model. It doesn't take all of the responses, the geomorphic responses into account. It's just a sort of snapshot, first look at what do we think sea level rise could do to our river shorelines. So if you didn't think sea level rise was a river problem, hopefully you will now consider it like that. The dark blue is then further modelling that they've done to look at if we had a 1 in 100 year storm and sea levels 1 in 100 years return interval out there in the ocean, what parts of our river catchments would get flooded. And this is serious stuff. This is across well-developed parts of our city. But these are the consequences of building on a Holocene progradational plain. So when I showed you the dynamic coastline before of Christchurch and how it's formed, this is all formed east of Riccarton across the Holocene. So when I say a Holocene progradational plain, I mean this very recent surface. Now, Holocene progradational plains, nice flat areas, are well developed in most parts of the world. So this is not a unique situation for Christchurch. This is actually a very common situation globally. Tokyo is another good example of a city built on a Holocene progradational plain. What about the open coast, the sand beach responses to sea level rise? They're going to respond differently to our rivers, and this is the second set of processes that I'm going to look at. So we've got a rule or a theory called the Brimon Rule. Now the Brimon Rule is recommended by the UN Environment Programme. It's in case law in New Zealand. It's probably the most commonly used model or idea to predict how sand beaches will respond to an increase in sea level. But it's a very, very limited theory, and it's often applied well outside the boundaries of where it should be. Let's just have a look at the rule first. So it says with a sea level rise, you will get a response in the equilibrium profile. So that's kind of a statistical average profile. It's not what you'll see at the beach every day, but over the long term is how the beach will look. And the profile will move landward and it will move up. So we will erode this part of the beach, our sand beach, and we'll use that sediment to build up the nearshore shelf and to accrete or build up the elevation of the profile. So this rule indicates that sand beaches, instead of just being flooded when you raise sea level over long time periods, like the IPCC time periods, it can respond by moving sediments about and by adjusting the profile. And they give one kind of idea about how profiles could respond. I think the idea about profiles responding and moving sediment about is a good one, it's a valid one, but I'm not entirely sure that this profile given by the Brimon Rule fits our local coast, because there's a few other factors. But in the Tonkin and Taylor report, for a 1 metre sea level rise up to 2115, they predict retreat of our shoreline from our open sandy coast, so the areas between here and here in this table, of about 50 to 70 metres, but variation between about 30 and 100 metres. So we're expecting shoreline retreat in response to the 1 metre of sea level rise that the IPCC and NEWA are predicting up to 2115. But hang on, we've had sea level rise. We've had sea level rise for the last century. So we could test the Brimon Rule by looking at the last century of sea level rise and see how good a fit it is locally. We've had 19 centimetres of relative sea level rise in Canterbury. Have we had profile retreat? Have we had shoreline retreat? At the moment, our beaches are pretty much stable to very slightly accreting, sort of 1 millimetre per year. I guess you can call that stable. So they are not currently responding to the last century of sea level rise in a Brimon Rule style manner. Maybe we chuck the Brimon Rule out and say it doesn't work, or maybe we just need to look at a few other factors as well. Maybe the Brimon Rule is too restrictive. One of the big limitations of the Brimon Rule is, apart from that it can only apply to sand beaches, it doesn't take account of very important factors such as the sediment budget and the wave climate. So the sediment budget and the wave climate play a big role in why we've got stable beaches in Pegasus Bay. Here, Pegasus Bay, our Christchurch coast, we're sheltered from a lot of very high wave energies coming from the Southern Ocean by Banks Peninsula. It's our big protector from the Southern Ocean swell waves. It doesn't protect the Canterbury Bight, and that's why this environment is much higher energy, and consequently you get much more gravelly beaches. So the wave climate is very, very key to the fact that we've got stable sand beaches in the lee or in the sheltered zone behind Banks Peninsula. We need to look at changes in the wave climate that we might expect over the next 100 years if we're going to understand the response of our beaches over the next 100 years. If it's an important factor now, it's going to be an important factor in the future. Another important factor is our sediment budget. This is the amount of sediment coming into and going out of our beach systems. It's a little bit like an accounting system for coastal geomorphologists. And we have a healthy sediment budget at the moment, fed predominantly by rivers, and the big star in our sediment budget is the Waimakariri River. So the Waimak plus a little bit from the Ashley, the Koe and the Wairau is pumping sand into our coastal environment, and enough sand of the right size to maintain that shoreline against the particular wave climate that we've got at the moment and the sea level rise rates that we've got at the moment to prevent it eroding. So we need to understand changes in the sediment budget, and the Tonkin and Taylor report in further pages does go on to discuss a little bit about this. But we need to sort of not look at profile response in a simple term. We need to put all of these system factors together to understand how our profile is going to respond, how our open coast sandy beaches are going to respond to accelerated sea level rise. And not all beach behaviour is related to sea level change. So here is a good example in New Brighton Spit. We've got a series of shorelines across New Brighton Spit from the 1950s to the present, in fact from the 1945 to present, which show how dynamic and how mobile the end of New Brighton Spit is. Now these natural kind of dynamics that you get in a spit system overlaid on the coastal management actions that we take when the spit moves. But just generally, you can see that in the 1950s, areas which are now developed in New Brighton Spit would have been in the water. So it's a very dynamic feature, and these kind of dynamics cannot be explained by the sea level rise alone that we had over the last 50 years. These are to do with sediment budget movements, these are to do with transport systems, these are to do with our wave climate, and the fact that spits are not landforms. Spits are coastal deposits of sediment that are naturally very mobile and move about. So if you regard them as a terrestrial environment, you can run into problems. What about globally? Brun's not enough to explain locally what's happened and perhaps what's going to happen to our coast. What about the global picture? Well, 70% of our coasts are eroding globally, and the average retreat rate is somewhere between 1/2 and 1 metre per year. If we were going to induce these kind of retreat rates, this kind of erosion, we would need sea level rise of about 20 millimetres per year to create that much erosion, just using sea level alone in a Brun-style equation. So if all of the erosion that we're experiencing globally was just down to sea level rise, we would expect to see sea level rise of 20 millimetres per year. But globally, we're looking at absolute rates of about 3 millimetres per year. So other factors are contributing to the erosion rates that we're getting globally, just as other factors are contributing to the stability of our present coastline. What are those other factors? Things like changes in the sediment budget. Humans have made massive changes to sediment budgets through impoundment of sediments and water on rivers in the form of dams, through changes in water abstractions, through hardening of the shoreline, through changes to catchments where we've hardened city surfaces, urban surfaces, where we've released pulses of sediment by deforestation. We often call the present era the Anthropocene rather than the Holocene. The Anthropocene to recognise that humans are really starting to be a very active and significant process in the landscape, and sediment budgets is a good example of that. Storms must also be a part of this equation, a part of the erosion that we're seeing globally. And storm clustering is a hot topic, looking at how closely together storms occur, because 2 or 3 storms, 2 or 3 small storms together can have the effect of one very large storm. Inappropriate development in very low-lying areas, development in the coastal system, development through sand beach systems, and I put in inverted commas protection works, things that we've done to try and maintain the line of the land, which lead to beach erosion. So there are lots of interventions, lots of human parts to this equation, as well as other natural parts such as storms. And then plus or minus coastal management interventions to slow erosion rates in different areas. So what I'm trying to do here is paint a picture of responses on coasts to sea level rise that are quite complicated and involve a number of different factors. I talked to a coastal scientist last week, and he just echoed what you hear at every coastal conference that you go to. Sea level rise doesn't create new hazards, it exacerbates existing ones. So we're not going to meet the sea level rise hazard next year or over the next 100 years. It's not going to be a unique new thing. What we're going to see is we're going to see existing hazards which are getting worse, and that's how we're going to notice base levels coming up. When we have base rises in sea level, the variation that goes on top of that, and if you could put that on top, that would be great. Thanks, Chris. He's got this job because when I did this earlier, I almost broke the beakers. So once we add our variation in on top of our sea level rise, This is how we're going to notice our mean water levels at the coast rising when we have events that come in across those higher base levels. Thank you. We've obviously accounted for that level of sea level rise. So this is the third part of my talk, and I'm going to look at multi-hazards, or different kinds of hazards, how they interact with sea level rise. And a nice example is flooding. So these are some of the maps that were published by Jacobs and SKM from an assessment of flooding that occurred in the Dudley Creek catchment. So if you've heard of the Flockton cluster, those people being flooded, this is that sort of area in between St Albans Park, Richmond Park, along this river system here. They've done an assessment of what flooding was like before the earthquakes for a particular flood scenario, and then after the earthquakes. And you can see very clearly here that there's an increase in the flooding extent post-earthquakes, because we've had changes in our land levels and changes in our drainage systems. These are the kind of hazards adding up together that we'll see with sea level rise. I've used an earthquake flooding analogy, but you can look at the same sorts of things happening with sea level rise. We've got a fantastic laboratory in Christchurch. I've said that Christchurch is not unique in terms of being a Holocene progradational plain, a very flat environment that's very vulnerable to sea level rise. And in 2007, Colin Woodruff identified these kinds of cities on Holocene progradational plains as very, very vulnerable to the next 100 years with the sea level rise. But fortunately or unfortunately, we've got a great laboratory for understanding that now, because we've had relative sea level rise. And the way that we've got our relative sea level rise is through land subsidence. So instead of our water going up with the earthquakes overnight, we've had our land subsiding. And this gives us a great opportunity to imagine what sea level rise feels like in some respects. It's not identical to what happens when the ocean water levels go up, but it does give us some indications. It's a good laboratory to come and study this here in Christchurch, because when you have a hazard that creeps slowly over very long time periods, it's kind of hard for us to understand the effects of that and to measure and statistically separate the impacts of that. But when you have something happen all of a sudden, you can see the effects in a much more dramatic way, so we can start to understand them. It's very unfortunate if that leads to flooding at your place, but it is a good natural laboratory for understanding relative sea level rise. With our land levels dropping, we've also come closer to the base levels of our rivers. Those rivers have changed in different ways to do with the earthquakes. They've reduced capacity because the banks have rafted together. The base has come up, so you've got less volume in your river channel. But we are a lot closer to the tops of our old stop bank levels, and we're a lot closer to the water levels in our rivers. So we are at the coal face in terms of understanding relative sea level rise in Christchurch. Now, tsunami, I said you could add all sorts of other hazards onto sea level rise. So, I'm not going to get you to pour it on top, that's okay. But just as an example of a hazard which interacts with the base level of our ocean, and if we're unfortunate, occurs on high tides when we've got ENSO type conditions that elevate sea level, perhaps when we've got a storm and when you've got a tsunami that arrives. This is when we really feel the pinch of sea level rise. NIWA's done some modelling to look at what happens in Christchurch with a tsunami scenario, that is a tsunami coming from South America, and they've used the 1868, which was quite a big earthquake in South America, produced a reasonably large tsunami. They've taken the largest wave from that tsunami and said, what if that was to arrive in Christchurch at high tide? Now, just a little bit of context, we had an earthquake in this very same region, in this very same fault area in South America last week. The earthquake was about 8.2 megawatts, whereas the 1868 was about 8.5 to 9. So it was a little bit larger. We had a tsunami coming across the Pacific last week, but it was a lot smaller than the 1868 scenario. But just to illustrate how active this area is in generating tsunami. The modelling here shows you wave heights in our nearshore environment. So this is not on land yet, it's just out in the coastal environment. But I put this map in to show you that embayments, narrow areas like Littleton Harbour, are our really most vulnerable environments to tsunami hazard, because tsunami waves grow and get amplified as they're funneled down embayments. But the estuary as well, this is our 1868 tsunami wave coming at high tide across the lowered land levels after the earthquakes. And you can see the vulnerable areas around the estuary. But these are areas that are vulnerable today. So this is an existing hazard, and this was a hazard before the earthquakes, just like flooding in the northern part of the estuary was a hazard before the earthquakes. And this is a hazard which, with sea level rise, we can expect to become worse. I've got a Multihazards project which looks at how hazards combine. And we started off with the earthquake scenario, and so here you've got seismic energy release, strong ground motion, and what happens to the stuff in between the energy being released and the surface. So what happens to all of that geomorphology in between? The soil deposits which liquefy, and the amplified ground shaking that you get through those waterlogged soil deposits. That's our Holocene progradational plain. The steep stuff like riverbanks, the sides of the estuary, the marine cliffs around Red Cliffs area that topple over. Now, I think the earthquakes are all about coasts and rivers. We get energy released, we get seismic energy released. But if we want to understand the patterns of change in our landscape and therefore the potential for damage in our built environment, the seismic energy doesn't really tell us much. We have to look at how that seismic energy goes through all of these deposits and how it interacts with the geomorphology in the surface layers to understand what's happening there. And here I've put in green the contributing river and coastal factors which tell you about the damage patterns or the change in our landscape. I've underlined the parts of this picture which relate to sea level rise. So, subsidence and lateral spreading, these things are only going to be felt more with sea level rise if they were to occur again. And they've given us our natural laboratory for relative sea level rise. The shallow water table. Our water table didn't go up very much at all with the earthquakes. Imperceptible change in that. But if you think about the level of that water table now with our subsided land, the dry crust on top above the water table is a lot thinner across large parts of our city. Now, liquefaction becomes a big problem when you've got an elevated water table compared to your land surface. If you have a nice big thick dry crust on top like out west in Christchurch, liquefaction is not a problem. But if you have a very thin dry layer on top, then liquefaction is a problem. So sea level rise can make earthquake hazards worse. And just the links between our earthquake complex of hazards, sea level rise, tsunami hazards, flood risks, shows you how complex understanding coastal hazards is. So hopefully with this diagram I'm illustrating that it's best if we try and understand not one hazard at a time, but we start to look at how hazards are related to make future predictions and plans for how to adjust our city. Now I'd like to finish off with one sort of salient diagram, and this is a diagram called Disaster Development Cycles, and it's by, it's a kind of an old truism in coastal science, but Bill Carter published it in 1989 in a textbook. So I'll tell you a little story. We become aware of a hazard, a risk, and we're uncomfortable about that hazard risk. And so, as a community, we go to our local authority and we say, fix that risk for us, do something, respond to it, because we're uncomfortable with this sea level rise hazard, this flooding hazard, this earthquake hazard, tsunami hazard, any of the ones that I've gone across today. There are different kinds of ways of responding to hazards. One of those ways is to retreat from the hazardous areas, so to step our development back from those hazardous areas. But other ways of responding to hazards, so with the recent flooding, there's been some articles in the press saying, dig the channels out, make the channels deeper, get all the water off the city, let's have an engineered response, build the stop banks up, put in pumps. These kind of engineered responses can alleviate the flooding hazard, for example, for a time, and we feel more comfortable. We're not so worried about that flooding hazard anymore. But that tends to lead to more development, more people, more infrastructure, more money, all at risk from the next natural event that comes along, which exceeds the capacity of our newly dug out channels, of our newly installed pumps. This is where long-term planning needs to have a whole package of responses. We can have some of those engineered responses for short-term alleviation of problems. But when you're talking about much longer-term problems like sea level rise that are going to occur over hundreds of years and that are going to impact large areas of the eastern parts of our city, they're not going to be permanent fixes necessarily. And so I'd just like to say, when evaluating responses to sea level rise in the pictures that I've shown you today, I think we need to look at different timescales. We can look at alleviating current problems, but we need to keep an eye on the longer term and plan for the longer term. Plan for our kids and our grandkids and what kind of city they're going to have to live in. If you want to know more about the Multihazards project, I've got two master's students working very hard, and Sue Young's here. She's an engineer and she's got great GIS skills looking at how lifelines infrastructure, like our drainage system, interacts with coastal multihazards, and David Holland as well with geotechnical skills is also working on that project. Or just go to the university's website, go to geography, and on our website we've got some media releases and further information about the Multihazards project there. So I've just put some references at the end of the presentation so that when that goes online, if you want to follow up on some of those reports and read the detail, because I've cut a lot of the detail out, I'm trying to give you a complex picture, but in a very short amount of time you can look in that. And before we have our questions, just to tell you that the next What If talk is going to be What If Hollywood Got History Right? And it's going to be by Dr. Peter Field. Thank you.